Hi friends, welcome to another video lecture of this present module. Now we shall learn how to find the PDF of the given random variable w. This is the continuation of the previous video. So please, if you have any doubts, please revise the things that have been covered in the previous video. So for finding the PDF of the random variable w, we assume that the PDFs of both x and y are already available to us. That is, we assume that both the PDFs of x and y are known to us. So the CDF for the random variable capital W can be written as FW, capital FW of W is written as probability of x plus y less than or equal to W. So this is the region over which x plus y less than or equal to W exists is shown in this diagram. Okay, this is the straight line. This is in slope intercept form. Right? If you remember, x by a plus y by b is equal to 1. That's the slope intercept form. So I have got x-axis, I have got y-axis here. So this is w comma 0. The coordinate at this point is w comma 0. The coordinate at this point is 0 comma w. So this is the line where x plus y is exactly equal to w. And beyond this line, this is the region where x plus y is greater than w. And below this left side part of the y-axis, this is the region that is where x plus y is less than w. So this is x plus y equal to w. So this is the region where x plus y is less than w. This is the region where x plus y is greater than w. So here I should have the region of integration, or here I should have the region R where x plus y is less than or equal to w. So I should have the region x plus y less than or equal to w. So that's why P of x plus y less than or equal to w is given by probability of the coordinates x comma y belonging to R. Okay, so that is given by now applying the two-dimensional integrals or the double integral concept. The probability of x comma y belonging to R is simply given by double integral R fxy of x comma y dx dy, where R is the region corresponding to the place in the graph where x plus y is less than or equal to w. So this is the region of integration. X plus y less than or equal to omega. X plus y less than or equal to w. So ಈ straight line ಕೆಳಗಡೆ ಇರೋ part so is the region of integration. So that's why now we will be doing only mathematics. Now x ranges from minus infinity to plus infinity. Now I should write this, I can write this in many ways. I shall stick on to one method. X, let me now double integral R fxy of x comma y dx dy. So R is the region. The region of integration is lying below the straight line x plus y is equal to w. Because I should have x plus y less than w and x plus y is equal to w also. So the region which is lying below the straight line x plus y is equal to w is the region of integration. The straight line ಕೆಳಗಡೆ, including the straight line, and the region lying below the straight line is the region of integration. Okay. So this is equal to double integral fxy of x comma y dx dy. Now x ranges from minus infinity to plus infinity. So when x is ranging from minus infinity to plus infinity, I need to find the region of, I need to express y in terms of x. That's how we do mathematically, right? So when the outer variable is ranging from minus infinity to plus infinity, right? So I have express y is equal to w. Now express y in terms of x. So here x is x is equal to minus infinity to plus infinity is the outer integral. Now the inner integral is with respect to y. X outer integral, y inner integral. But when I am expressing y, express the integration limits of y in terms of x. That is, express the limits of y in terms of the outer integral limits. So y also ranges from minus infinity to plus infinity. So y ranges from minus infinity. So x is ranging from minus infinity to plus infinity. So y is ranging from minus infinity to the upper limit is y is equal to w minus x. You express y in terms of x. So y is equal to w minus x. So that's what I have here. So integral minus infinity to plus w minus x is the inner integral with respect to y. Y limit ನಾನು xl express ಮಾಡ್ತಾ ಇದ್ದೀನಿ, so that the integration becomes more clearer. This is how we do in double integration, right? So I am doing the same mathematics here. So So it is integral x is equal to minus infinity to plus infinity, integral y is equal to minus infinity to w minus x, fx y of x comma y dy dx. Okay, so call this equation 64. He has repeated it. So call it equation 64. Now we know that the PDF is obtained by differentiating the CDF, right? The above equation, this equation can also be written as, now this is the CDF that I have obtained. This is the CDF that I have obtained. This probability of x plus y less than or equal to w is on the left hand side is nothing but the CDF, because probability of x less than or equal to x is the CDF. So extending the same idea to 2 dimensions. So I recognize that probability of x plus y less than or equal to w is nothing but the CDF of w, that is fw of w. So fw of w is equal to integral minus infinity to plus infinity, integral minus infinity to w minus x fxy of x comma y dy dx, which I have called as equation 64. Now if I differentiate the CDF, I get the PDF. So let me differentiate both sides. So if I differentiate both sides, I get fw, small fw of w, which is the PDF, is equal to integral minus infinity to plus infinity fx y of x comma w minus x dx. Here I have used the Leibniz rule of differentiation under integral sign. Okay, that you would have studied in your M1, M2, and M3, right? The same idea I am using it here. If I am differentiating the integral both sides, right? There with respect to y, then I get this one. Then I get the PDF. If I differentiate the CDF, I get the PDF. So differentiating both sides and applying Leibniz rule of differentiation under integral sign, I get fw of w is equal to integral minus infinity to plus infinity fxy of x comma w minus x dx. So since x and y are assumed to be independent random variables, I have the PDF fxy of x comma y, which can be expressed as the product of fx of x and fy of y. So as a result of which, the result becomes the previous equation can be written as fw of w is equal to integral minus infinity to plus infinity fx of x into fy of w minus x dx. I am assuming that x and y are independent random variables. So if x and y are independent, then I can write fxy of x comma y as f of x into fy of y. So applying this principle, this integrand fxy of x comma w minus x can be written as fx of x into fy of w minus x. So that's what I have done here. So I have written fw of w is equal to integral minus infinity to plus infinity fx of x into fy of w minus x dx. Call it equation 65. So this is nothing but the convolution integral. This is nothing but the convolution integral, or the right. So by using the convolution property, and I also know that the convolution integral is commutative in nature also, right? So that's why I can write this equation 65 as an integral in terms of y also. Here I have written in terms of x, but it's a definite integral. A definite integral is independent of the integrating variable. That is integral a to b f of x dx is given by is also equal to integral a to b f of y dy also. So since using the definite integral property, I can write this as fw of w as integral minus infinity to plus infinity fy of y fx of w minus y dy also. I am replacing where x is there by y. I can replace x by t also, not an issue. Now, by looking at this and recalling that it's a convolution integral, I can conclude that the fw of w, the PDF, is given by the linear convolution of fx of x with fy of y. So that's why I can write this as fw of w is equal to fx of x convoluted with fy of y. Since convolution is commutative in nature, I can also write fw of w as fy of y convoluted with fx of x. Here the star symbol designates convolution. Star symbol designates convolution. So that's why the PDF for a random variable w is equal to x plus y is the convolution of the PDFs for x and y. Okay. Similarly, we can calculate the characteristic function of the w also. The Fourier transform of a PDF gives me the characteristic function. The inverse Fourier transform of the characteristic function gives me the PDF. The PDF and characteristic function form a Fourier transform pair, as it is well known. So take the Fourier transform on both sides. I get phi w of j omega is equal to double integral minus infinity to plus infinity fx of x into fy of w minus x dx into e to the power of j omega w dw. I am taking the Fourier transform on both sides of equation 65 here. I am taking the Fourier transform on both sides of equation 65. So phi w of j omega is equal to double integral minus infinity to plus infinity fx of x into fy of w minus x dx into e to the power of j omega w dw. Call it equation 68. So let me change the order of integration. So the inner integral is with respect to x. The outer integral is with respect to w. Now the inner, I shall pull the inner integral outside when I am changing the order of integration in the next step. That's what I am saying. In the next step, I am going to pull the inner integral outside and I am going to push the outer integral inside. While I am pulling one integral outside, I shall also pull some variables associated with it. When I am pushing one integral inside, I shall also push some variables associated with it. So when I am pulling this integral, the inner integral with respect to x outside, I shall also pull fx of x also outside. So that's what I have done here. Integral minus infinity to plus infinity fx of x. Now the outer integral with respect to w, I shall push it inside. So when I am pushing it inside, I shall also put some variables also inside along with the integral sign. So the inner integral in the next step would be consisting of fy of w minus x into e to the power of j omega w dw. That's what I have here. Now the outer integral is with respect to x, the inner integral is with respect to w now. Now let me put, this is the integrals, double integral that I have obtained after changing the order of integration. Now let me put v is equal to w minus x. So if I put v is equal to w minus x, v is a dummy variable of integration. So w can be written as v plus x. Okay, and dw is equal to dv because x is fixed here. dw is equal to dv because x is fixed. And if w is equal to minus infinity, v is also equal to minus infinity. And if w is equal to infinity, v is also equal to infinity. Okay. So due to this, the characteristic equation can be written as integral minus infinity to plus infinity fx of x dx into integral minus infinity to plus infinity fy of v e to the power of j omega into v plus x dv dx. Now split this exponential into product of two exponentials. So this becomes integral minus infinity to plus infinity fx of x into integral minus infinity to plus infinity fy of v into e to the power of j omega v into e to the power of j omega x dv dx. Now this can be written as product of two integrals. So integral minus infinity to plus infinity e to the power of j omega x dx multiplied by integral minus infinity to plus infinity fy of v e to the power of j omega v dv. That is, here the inner integral is with respect to v. The inner integral is with respect to v, that is dv. Now e to the power of j omega x and dx are constants because the inner integral is with respect to v. So that's why I can pull e to the power of j omega x and dx outside the inner integral, but within the outside integral. ಅಂದ್ರೆ e to the power of j omega x dx ನ ಆಚೆ ತಗೊಂಡ್ಬರ್ತೀನಿ, ಯಾಕೆಂದ್ರೆ ಇನ್ನರ್ ಇಂಟಿಗ್ರಲ್ ವಿ ನಲ್ಲಿ ಇರೋದು. ಸೊ ಆಚೆ ತಗೊಂಡ್ಬಂದ್ರು ಏನು ತೊಂದರೆ ಇಲ್ಲ, ಅದನ್ನ ಆಚೆ ತಗೊಂಡ್ಬಂದು fx of x ಜೊತೆ ಸೇರಿಸ್ಬಿಡ್ತೀನಿ. So that's what I am doing here. E to the power of j omega x into dx I have brought outside. So this becomes integral minus infinity to plus infinity phi x of fx of x into e to the power of j omega x dx into integral minus infinity to plus infinity fy of v e to the power of j omega v dv. But what are the definitions of this? The first integral is the characteristic function of x. The first equation is the characteristic function of fx of x, that is phi x of j omega. The second integral with respect to v is the characteristic function of fy of v, that is phi y of j omega. So I replacing these integrals by this corresponding phi x of j omega and phi y of j omega, I infer that phi w of j omega is equal to phi x of j omega multiplied by phi y of j omega. That is, the characteristic function of w is the multiplication of the characteristic functions of x and y. Okay, this is one of the famous Fourier transform properties that is used for this purpose. And Fourier transform itself can be defined in many different ways. Okay, so please remember, that Fourier transform itself can be defined in many different ways. We are following the symbology as per your prescribed textbook. Okay, thank you. Problems we shall solve in the next video.